Hey, what's up guys? The Lone Top 10's here with another awesome Top 10 just for you. Ancient cultures like the Chinese and the Greeks looked up at the sky in awe and racked their brains to figure out just what was going on in space. They made remarkable breakthroughs, but things were really ramped up in the 1900s and the 2000s as technology had advanced. Some of those discoveries might be unfathomable to the non-scientists out there, including you guys who go on YouTube and are not astronomers or anything like that. But guess what? They're currently real. So anyway, here are the top 10 things going on in space that will melt your brain. First off, we'll start off with number 10, curved space. The idea that space can be flat or curved is strange and maybe not even believable, but alas, it's true. Albert Einstein realized the space around gravitating objects is curved, which accounts for things like orbits. More on that next. Alright, one way to determine whether space is flat or curved is by testing Euclidean geometry in these spaces. This is geometry performed by Euclid, a mathematician from ancient Greece, that wrote up all the formulas you learned in high school geometry. Those older YouTubers out there. For example, in Euclidean geometry, a triangle's angles add up to 180 degrees. Non-curved space. It's because the curvature of the straight lines, what an oxymoron, alright, causes the angles to be bigger. You could draw a triangle with 390-degree angles. Think about that for a minute. Alright, next up, number 9, the not force of gravity. Remember in high school physics when you learned Isaac Newton's 3 laws of motion and the force of gravity? Well, force is mass times acceleration, or 9.8 meters a second squared. Forgot it? Well, almost. Newton was not completely wrong with his laws about gravity. However, he wasn't completely 100% accurate. Turns out in his formulas, you could theoretically get answers like the potential for infinite gravity that just don't add up, and Albert Einstein saw that. Then he came up with his own equations that answered questions about gravity that Newton's equations couldn't. This is how we get curved space, which causes the phenomenon of gravity. Imagine space as a rubber sheet. Now stick a bowling ball representing Earth on it. You should be seeing a curve in the rubber around the Earth. Keeping this in mind, if you were to roll a smaller lighter ball or the moon at the edge of that curved rubber, it would get caught in the curvature of the rubber, or gravity, and go in circles or orbit around the Earth. This is how gravity works according to Einstein. The big takeaway here? Gravity is not a force. So forget high school physics. Just throw it. Only that part. Anyway. Number 8. Einstein's theory of relativity. Einstein's theory of relativity is a complicated one. So hang on to your hats, boys and girls. This one plays in with curved space and gravity not being a force, but it is by far its own animal. On larger scales, it's an object moves from an observer. Time slows down to the observer. For instance, if you hold a clock in front of you, the seconds will tick like normal. Move that clock further away, and those seconds and minutes, to your perspective, will slow down. They don't really slow down, but they do look like they're slowing down. This goes for all kinds of things, like agent and light. If you hold a blue light in front of you, it will look blue, but as it moves further and further away, it will start to look red, because red has a longer wavelength. That's why we got those rainbows, by the way. That is also why the pitch of sound, like when you hear a train horn, changes. As it gets closer, the wavelength shrink, so the frequency and the pitch go up. As it goes away, the wavelengths get longer, and the frequency and pitch drop dramatically. On Earth, these relative differences are very subtle, almost negligible, which is why Newton's laws are used and taught in school. They serve their purpose just fine on Earth, except in one respect, global positioning systems. GPS devices use Einstein's relativity to function properly. Time at the satellites above Earth pass slower to us than it really does, and for the satellites, time moves faster down here due to Earth's gravity. These time differences are great enough that they'll completely throw off your travel time. To make sure we get to where we're supposed to be, GPS devices rely on Einstein's time. So thank Einstein for GPSs. Although he didn't actually create the thing. Alright, number 7. Black holes. Black holes are still a great mystery even today. Their very nature is what makes them so difficult to understand. For one, you can't see them. Their gravity is so darn strong, nothing can escape, even light. Matter would have to move faster than the speed of light to get out of the grip of gravity, called the escape velocity, which is impossible. This is how black holes got their name. No light comes out of it, so we can't see it. Therefore, it's black. Simple. Except they're not so simple. Black holes are a sort of stellar carcass. When a massive star, much bigger than our sun, dies, it blows up into a supernova. It will collapse into a neutron star or a black hole, the latter of which is completely unlike a star. Black holes have an extreme gravity that leads to a singularity where there is infinite density, where all the mass is packed until, well, you know, and that's where time stops completely. The event horizon is a point of no return on the outer part of the black hole, where the escape velocity exceeds the speed of light, and space and time move in one direction, forward. Once you cross into the event horizon, you're not coming back. If you get to the singularity, you will die an ugly but quick death. Because the tidal forces are so strong, your body would be unnaturally elongated, and you'll be crushed front to back and side to side. You'll end up looking like string, which is another reason why we don't know much about holes. It's just too risky. We won't throw someone in there. That's just murdering. Number 6. Alternate universes. This one does sound like pure science fiction, but is a legitimate concept that scientists have grappled with for a century. During World War I, Carl Schwarzschild wrote up the first equation about black holes. Like their radii, and even more fascinating what's inside, he wrote that at a single instant, the singularity, the point of depth that crushes you, connects to an infinite parallel universe, completely independent of, but within our own universe. Even crazier is what a man named Roy Kerr wrote. His words apply to a rotating black hole that makes a world, or technically worlds, of difference. His equations turn the singularity into a ring instead of a dot. This ring is almost like a portal that will lead to an infinite universe. Well, infinite universes. If you want to go through the singularity without touching the ring because you'll die, you'll go into another space somewhere else, and should not come back through that same singularity to the space whence you originally came from. The space is that you would enter would be inside a white hole that, as the name suggests, is the total opposite of a black hole, in that nothing can come into it but can slowly spew out. In theory, you could go out of that white hole and be in a universe just like ours, but isn't ours. If you wanted, you could find another black hole, go in, and come out of the white hole in the third universe. You can repeat this process forever, if you want to. You'll just have to suffer the consequences. Of course, all this is just in math, not reality. While it probably is not true due to factors like atom mass, it is a concept that scientists have to take seriously and deal with even today. Just think about it. Number 5. And speaking of white holes, guess what? Number 5 is white holes. Well, a white hole is the complete opposite of a black hole, like I just mentioned, because nothing can exactly go in. It is structured just like a pure black hole, though, in that its singularity is ring-shaped and acts as a gateway to other universes. It does have an event horizon as well that does not allow those who cross it to come back inside because space and time are that strong. Excuse me. There are no white holes in our universe. These are purely hypothetical and come with the math behind black holes. Even if hypothetical, white holes existed in hypothetical universes in hyperspace, so we would not be able to access them simply due to the nature of black holes. If black holes weren't strong, then we could go into a white hole. Simple. Number 4. wormholes. These are also results of the equations behind black holes and white holes, but don't necessarily have to do with alternate universes and hyperspace. Instead, these deal with our own universe. According to the equations, these wormholes could connect space-time as a shortcut. To visualize this shortcut concept, imagine a giant block of concrete in front of you. To get directly to the other side, you have to go around it. The straightest route you could possibly take is to walk directly to it and rub your shoulder along the edge of it as you walk around it. To make it shorter, you could just cut a hole in the concrete and go through it. Same place, seeing the universe, but a different and very difficult way. Of course, there are many technical aspects wrong with this analogy, but it gets the point across. Wormholes could cut through some weird space-time to get from one part of the universe to another without having to travel through the space-time of the universe itself. Wormholes start with a black hole and spew out of a white hole somewhere else in the universe, but as a lot of this is still pretty hypothetical. The fact that it is under serious scrutiny is mind-blown enough. Number 3. Dark matter. Less brain-melting but still puzzling and crazy is that there is so much stuff in the universe. But the catch? We can't see it. We don't know what it even is. And it's everywhere. That's all we know about dark matter. The substance makes about 27% of the universe. That is more than a quarter of the universe. And dark energy, something totally unrelated, but just as mysterious as dark matter, makes up the 68%, more than 2/3 of the universe. Normal matter, like the protons and neutrons are made of, makes up only 5%. Dark matter was discovered by Vera Rubin when she realized the total mass of galaxies was more than the mass that the detectable objects in the galaxy should be added up to, or should have added up to. That means that there is something in these galaxies that can't be seen or detected that has mass. How can that be? Why? What is this stuff? These are questions that mess with astronomers' brains every single day for the same reason they puzzle ours. This doesn't even make sense, people. Just think about it. Number 2. Whatever it is the universe is expanded into. Alright, along cosmological lines is another big question. What is outside the universe? Many know that the universe goes on forever and ever. It has no edge and no center, but is constantly expanding. That is, the space between galaxies is growing. This can be seen in the redshift of nearby galaxies. Redshift happens when an object is moving away from us. Therefore, its wavelengths of light are getting bigger, so the lights get redder. So the universe is expanded, but what is it expanding into? What is on the other side of the universe? This concept is mind-boggling and currently difficult to fathom, but this is real life. Just want to let you know. Number 1. Gravitational lensing. This last one is perhaps the least mind-boggling, but it still makes you scratch your head. Also, unlike the others on this list, it has been proven, but that doesn't make it any less crazy. Gravitational lensing is when you observe an object to be in some position in space, but it isn't there. This is because the light being emitted from its actual location is being refracted due to the gravity of an object as in the way. Gravity bends light, so guess what? Chew on that one. Alright guys, that is it. Hopefully, if you have any other things that will melt your brain that I have not suggested in this video that is related to space, let me know in the comment box below. Don't forget to subscribe to this channel, like this video, and see you guys next time. Take care.